of last year, until the end of last year, well, 2020. We were working at the European Space Agency in the Netherlands, in the Planetary Robotics Laboratory. So since this is an ESA presentation that we made during our time there, and we no longer work at ESA, we have to do some rebranding. So now it's an ExoMy presentation, and the official ESA logo is gone. And Max actually now works as a propulsion test data engineer in the rocket factory. And I'm currently a mechanical engineer at Integrity, which is a very small freelance company, and we work in aerospace and laboratory automation. Good. So a bit more about the project. You have to imagine a bit the ESTEC site, which is the ESA technology site in the Netherlands. It's one of the biggest ESA sites, and every year there is an open day. So people, I don't know, maybe 10, 20,000 people from the Netherlands and Europe, they can come and visit all the facilities and they can walk around. And the purpose of European Space Agency is also to motivate and bring space to the population, to show them the benefits of doing space research, of developing technologies, and to give them a nice hands-on experience and bring them closer to this abstract topic. And here you see actually a little bit the Planetary Robotics Laboratory. It's a Mars yard, as you see here, with different terrains, 9 by 9 meters. And we have Mars rover models, as you see here, which are fairly expensive. Maybe this costs 100,000 euros, on which we used to develop, and they still develop, codes, and on which they can test algorithms that are used on the mission. But on an open day, it's not very interactive for the people. And you see there's a lot of kids here, and they cannot control the Mars rover that's 100K, because it's just dangerous. So we come up with different ideas. You see here, this is a spherical air bearing. It's a ball that is floating, and this the kids can interact with. It's made for that. And wait, now we skipped a few points. But we would have liked, we wanted to develop a rover that kids can drive around and that fulfills these requirements here. So it should go further than just for this open day. It should also be open source, so, and accessible to people so they can build it. And so it should be cheap. There we come from, because it should be cheap, we decided it should be 3D printed and not use any specialty tools or metalworking tools. You don't even need a drill to build it. We wanted to appeal to a wide range of people. So we want to have a friendly robot and not maybe an evil looking robot. And by the time that we were developing this project, ExoMars, the European rover that is going to fly to Mars, was just about to launch. This was the same year where the NASA Perseverance rover launched, and there was a window to launch to Mars. So we wanted to also take this window at ESA, but then due to COVID and other reasons, the project got delayed. But we were aiming to push out the project so we can use the project to promote ExoMars. So it's very similar to ExoMars and inspired by it. And as mentioned, the project is open source. The first prototype and the first idea of this project was actually already in 2018. You see here my colleague Shankar. And this was kind of the proof of concept that you can build a 3D printed rover in a very small scale for low cost. This worked, but it was not working amazingly. It worked for the open day, but not more. Afterwards, it was broken. So then the next year, we did some changes. with the product, but as you see, it's still a lot of cables that are just tangling around, and a lot of loose contacts can occur. It's not stable. It worked at the open day in 2019, but then it broke afterwards pretty much immediately. So it was also not good. So after this open day, we decided, okay, we will redo everything, and we will design it completely new from scratch, take what we learned and make it clean. And that's what we did. So you see here the previous prototypes and then the improved prototypes. There were no components that have to be glued together, no components that have to be duct taped together. All the zip ties and cables, they are hidden, and it's made to be reproduced. And then we were done. So the design was finished, but this was only one part of the project. The other part of the project was, of course, the software and the documentation. You see here a bit how the generations changed, how we went from something that barely drove around to a reliable product that you can actually operate for quite a while without anything breaking. I mentioned the resemblance to ExoMars. It was important for me. I did the mechanical design, Max did the software design. So it was important for me to pick up characteristic design features of ExoMars in order to promote ExoMars and in order to make the connection with ESA. So you see here the solar panels have this U-like shape. We scaled it down. Then we have the triple boogie suspension. I'm going to talk about that afterwards. And we have the drill. This drill, you will see later, it's not actually a drill, but it still has a purpose and has a functional use. And then the wheels, while we don't have flexible wheels because it's not necessary, we took over this spline design. Now for roboticists, this is interesting. You might know from the NASA rovers, the rocker boogie system, where you have on both sides of the rover, you have two linkages with pivot points. The ESA rover actually uses a different system that is simpler and performs equally as well. So this is the triple boogie system. You see here, you have the front and center left steering motors and wheels. They are connected with this rigid bar, which pivots around the center point. And there is no spring, there is no differential, there's no motor here. This is just a simple pivot joint. And then we have the same on the right side, on the other side, with this bar that can pivot, and we have the same on the back. And because we have these 6 wheels and these three linkages that can pivot, the whole system is stable, and we don't need to use any differentials as you have on the rocker boogie, which introduces complexity. And because you have these linkages that can pivot, it leads to equal forces on all wheels, which helps greatly to drive in rough terrain and over large obstacles, as you will see later.
Miro, just a quick question. Do you have a chat window open on your end there?
Actually, no.
Okay. Yeah, people may ask questions. Nobody has done it yet, but in case somebody does.
Sure. Yeah. But in the anyway, there's time in the end also to ask questions.
Sure.
Sounds good. Good. Then now a bit of the specs. I didn't translate it to freedom units, but maybe you also work with metric sometimes. So it's around 2.5 kilograms heavy, which is approximately the weight of a cat, I think. It's about the size of a cat. I like this analogy more than these measures because it's hard to imagine. And depending on the battery you use, you can actually get quite a decent battery life out of it. So at this open day where we had visits from morning till late afternoon, we had to change the battery once in the middle, and we were driving basically non-stop. So it's quite a lot of endurance. Looking now a bit closer in the system, As mentioned, with the triple boogie, the cables are actually wired here internally. There's a little lid you can put on top of this bar. Each of the 6 wheels is actually driven, and each of the 6 wheels is also steerable. And that is different, again, compared to the NASA rovers and the NASA rover derivative rover models. There are some open source model rovers. For example, there's the NASA open source rover that they provide, but that costs like $2,000 and has a lot of metal parts and sheet metal parts that you have to buy. And then there's the SAW rover, but they all only have 4 steerable wheels. So you're limited in your mobility compared if you have 6 steerable wheels. I mentioned that we want to appeal to young kids that are maybe 5 years old or 3 years old, that they can interact with the robot, as well as older people that want to program maybe the robot. And this is one of the way that we do that. So you have this hat that you can just put in the hat. You can customize it very easily with minimal CAD knowledge. And you can also move around the eyes there with a friction fit or a form fit. And then depending on how you kind of, how you how you put the tolerances between the eye, the pupil and the eye white, either they stay in place or they act like googly eyes. So we have actually 2 versions, I think, in the GitHub repository, depending on how you want to do it. And so then you can, a small kid can customize this rover, and someone a bit older can program it. And that's for me the appeal in this project. Then next, these wheels with the grousers. So the grousers are these little spikes that you see on the wheels. They work great in this sandy terrain that we were operating in. But once you go on a hardwood floor, for example, it starts to bump and jump around. So in this situation, we designed some wheel sleeves that are printed from flexible TPU material to have kind of like a tire effect. And then we added some switches just so you don't have to open anything, screw anything open, and you can just activate the Raspberry Pi with the main switch and then the motor with the small toggle switch. Now looking inside, I mentioned that we wanted to really use off-the-shelf components that are available all over the world. So we took very simple decisions. We put in a LiPo battery. I would not recommend using a LiPo battery now, since we learned a bit. So I would recommend a lithium iron battery because it's safer. But you can put in whatever you want, and it drops in very easily. And we put in a Raspberry Pi 4 with a PWM servo hat on top from Adafruit, so that's available everywhere for everybody. And then with a Raspberry Pi camera on top, very standard stuff. And then there's 2 DC-DC converters, which we'll talk about here. So we have this battery, which in this case provides around 12 volts. And then with the switches, and then we actually noticed we need to have 2 DC-DC converters, one for the Raspberry Pi, which is here, and 1 DC-DC converter to power all the servo motors. And then with this, that's really the nice thing with this PWM board. You can just take your servo motor, you buy a servo extension cable, you plug it in, and that's it. You don't have to do anything more. So it's a very simple setup process. Because we wanted to make this project very available, it was also very important to make the software easily available and very easy to install and use it. And I don't know if you know ROS. This is the robotic operating system. It's kind of the standard framework for robotics in academia and industry sometimes. And this is what we both used a lot, Max and I, and we wanted to use it for the rover because with this framework, you can also easily plug in new components. You can add a sensor, and there's probably already a component for that reads out this sensor, and then it can directly communicate with all the other nodes in ROS. So it's very easy to extend if you have something in ROS. Now the challenge is every ROS version works on a specific Ubuntu version, and only one specific Ubuntu version. But if you want to install a specific Ubuntu version on a Raspberry Pi 2, 3, or 4, you will struggle a lot. Maybe you get lucky and you have a happy shot that it works, but oftentimes it doesn't work. So what we do is we use the tool Docker, which is basically very lightweight virtual machines. And with Docker, we run our specific Ubuntu version that we need for our specific ROS version on any kind of Raspberry Pi OS. It can be any OS, as long as it's Linux, that runs on the Raspberry Pi. So it doesn't matter if next year the Raspberry Pi 5 is going to come out. You can still take our code that we developed 2 years ago, and it should run immediately without any porting issues. Good. Then we implemented some basic control algorithms and features. So you see here, it's possible to control the rover using this gamepad. At the same time, the camera can be live streamed to a web application that can be operated from the tablet or from your browser or from your phone. And in this case, also, it's possible that ExoMy hosts its own hotspot, so you can easily connect to it with your mobile device. Now, ExoMy has 3 locomotion modes. You see here he's turning like a car, driving a curve around the point. Now he's doing a spot turn. And finally, the last locomotion mode, which is unique to ExoMars and the 6 steering motors, is the grabbing motor. So you see he's not rotating, changing the orientation of the rover. He's just changing the position of the rover. Good. I mentioned the open source aspect before, and that was very important for us. So after we finished the design and testing phase, we set out and we wrote a very extensive wiki where we describe everything from purchasing instruction over how to install the software, how do you assemble everything, what do you have to manufacture actually, which is not so much. It's only the electronics that you have to assemble, manufacture, and the 3D printing. And then finally, how do you build it and how do you use it? It takes around 2 weeks to print, and these 2 weeks I put them in a way that if you start today, you will probably finish in 2 weeks. That's how it was, let's say, estimated. If you have a lot of printers, it goes quicker, of course, but and the assembly time depends also on your skills, but we estimate it's 2 days approximately. And yeah, a lot of people actually use different components. So you have actually quite a wide range, and depending if you buy original parts, for example, the Raspberry Pi camera, or you buy something from Alibaba, you can really have a wide range of costs that occur. And yeah, we wanted to show here some videos showcasing the climbing capabilities of ExoMy, and here you see very well the triple boogie locomotion system in action. You see, I mean, this rock is the same size as the wheel, and it just drives over it and continues as if nothing ever happened. And we had a bigger rock. And these are off-the-shelf parallax servo motors, continuous rotation servo motor, so it's not like some high-end super high torque stuff. Good. And this is also terrain that is often on Mars found. This is kind of a bedrock simulant, and even this, it manages quite well. Now this is actually the Hall of Fame for ExoMy builders. So Eric, after we published the project, after 2 months or 1.5 months, he just sent us a picture. I built it. We didn't expect that. The first guy just built it without any guidance, and very happy that it happened like that. And in the meantime, actually, there's a lot of people. We estimate around 30 people that built it. I'm in my current job, I'm also manufacturing 6 ExoMy for a client who wants to do a course with them. And there's quite some universities all around Europe, and also actually maybe also in the US. I don't know about that. But there's some universities that build them and then modify them and use them for student courses to really, because it's a good foundation to build upon. And so I'm hoping that maybe someone has an idea who could build it, another one, and or you want to build one. So if you want to build one and join the ExoMy community, we actually have a Discord server with around 200-300 people in there, I think, by now. And so if you have a problem or an idea or a question, or just want to share your progress with the ExoMy build, or see how they are doing, you can go there and they will help you out. It's really self-sustaining, and I think that's really what I'm very happy about. I don't have to answer every question. No, the community answers the question and grows actually independently of me doing things, and I think that's really amazing. So thank you very much. And you can find more like on our GitHub link, and I will post it also in the chat.
All right, thank you, Miro. Anybody? Let's see. There was a couple of questions that popped up in the chat there. You want to take a look at those? And
yeah, I'll have a look. 1 second. I'll stop my sharing. I will reshare if I need the slides.
Yeah.
There's already a link. I see. Perfect.
Yeah, I tried to kind of post some of the links as you were tossing them out there. So
perfect.
Yeah. So
let me just start on the top.
Yeah, go ahead.
Well, you can ignore my question about the center wheels. Now that I see the crab motion, I understand why those rotate.
Okay.
So
I was also amazed that the front of it doesn't rotate side to side more. But I'm kind of curious why, because the front seems to handle like rolling over a rock on one side really easily. Why is the rocking motion of the back 2 wheels really needed? Is that actually necessary, or could that just be skipped?
You mean it could also be fixed?
To the body, yes.
I think it helps to, so if you have them fixed directly to the body and you have a force here, then the body will not stay stable. So then you will tilt the whole body. And
oh, okay. So after the front wheels go over the rock, then as the back wheels going over the rock, that would tip it over. Yeah. Okay, thank you. That helped me to understand.
Does anyone really know Ross? We all try, but Ross is user-friendly. It's just very picky about who it's friends with. Yes, I do know Ross. I did quite some work in Ross. I mean, it's great if you have a bigger project. So if you have a lot of big sensors that you have to work with, and motors, and if you want to do networking, you also can do it, especially with ROS 2, it's much easier. I think the Python version is also easier than C++, and I agree it can be quite complicated to get into at the start, but I think it's worth it long term. It's a useful skill to have, definitely. You mentioned the drill-like protrusion on the front had a function. Ah, yes. Good, I can show you the function actually. And let me just share my screen again. Good. Share. So the function of the drill. Okay. Here. So what you can do, you see it here in this picture, you can remove the drill just with you have these 4 slots where it kind of hooks into, and then you remove the drill without any tools, and then you have this compliant clamp that you can push up, and then you pull the battery out to change it. Furthermore, you have here an access port where you can connect your HDMI cable, or if you want to power your external, if you want to power the Raspberry Pi externally, you can also connect your power cable here, unplug the battery, and then you connect your USB charger for the Raspberry Pi. So that's the function of the drill. It's a cover for the electronics access. Yeah, and this cutout actually works for both the Raspberry Pi 3 ports as well as the Raspberry Pi 4 ports. Let me check if there's more questions.
Yeah.
How do I even see the chat? I'm such an amateur, huh? Here, chat, more. Chat, okay, I have it.
Somebody
Ross.
mentioned if it was ROS or ROS 2.
So we did the implementation here, I think, on ROS, but while my other project was actually to transition the whole code base from another framework to ROS 2. And I think we also have a ROS 2 branch. So ExoMy has both ROS and ROS 2. What would you suggest learning? I think, okay, it's a tricky question. So I think learning ROS is easier than learning ROS 2 because you have a lot more tutorials and you have a lot more information and knowledge and projects that work with ROS. ROS 2, on the other hand, is the future, probably, you never know, but I think ROS 2 is the future. It has a lot of improvements architecturally over ROS. So yeah, I think if you want to start from scratch, and you don't need necessarily, let's say, a lot of drivers that are already existed, and you don't mind a little bit of a challenge, then I would probably start with ROS 2, because otherwise you have to relearn a lot of stuff and transition again your code base. So I think I would go with ROS 2. But if you buy something, I don't know, a kit that runs with ROS, or you just want to be the quickest and want to be the quickest at having a result, then maybe ROS 1 is better. Yeah. How much weight can the bot handle? It's not really made to carry payloads. The 3D printed parts here, the wheel brackets, they are not the strongest ones. Let's say it like this. I think this part, as well as the bearing here, where it's suspended and mounted to the frame, these two are the most prone to breaking. But if you go to the Discord, I don't know, you have quite some people that already put payloads on top, or maybe I have it in the presentation, you know. Let's see. People put stuff on top, but it's not made to carry heavy loads, so I don't actually have a number. Let's see if we see something. No. I know some people put solar panels, some people put sensors, more cameras. Yeah. Except, can the solar cell option be made to work? Yeah, this is a discussion that came up many times already. So I think we have someone in the Netherlands that built an ExoMy with solar cells. I think that is completely self-sustaining. So it definitely, I don't think he wants to connect it to power. He just lets it charge up with the solar cells. Yeah. And the max velocity tank depends a lot on the motors you use. I never really measured it, but it's like this. This was the max velocity with these motors. These are the parallax motors. Yeah, because it was made for us, we didn't use it as an academic research or as robotic research. It was almost like a toy. So we did not really characterize the speed and these specs so much. The latency between the gamepad controller and the bot is actually, I don't have a number, but it's an off-the-shelf Logitech controller. And I think it uses Bluetooth or something similar, maybe radio, and it works very reliable. I never had an issue with latency. You have more issues with latency if you go via the web interface. There you have maybe, I don't know, 200 to 500 milliseconds latency, but with the controller, it's really very, very, very smooth. Thanks.
Do you know about how much it costs to make the project, all told, all the parts?
Yeah, definitely. As I mentioned before, it depends really what components you use. So let me go to this view here. The biggest cost driver is from the electronics point are the motors, because you have 12 of them. So if you save $5 on the motors, then it's $60 there. Then the other big parts are the Raspberry Pi and the battery, which can easily, now with the supply shortage, it can be easily like $50 to $100. But maybe you already have a Raspberry Pi 3 laying around, or you don't need even the 4. You just get the 3, which can be found very easily. And if you don't have a time pressure, you can order a lot of stuff very cheaply from China, Alibaba. And then I think you can build it realistically maybe to, let's say, if you want to really save money and change the motors to cheaper ones, which I'm not sure I would advise, then you can build it maybe for $200 to $300. And if you want to use some better motors, then maybe it's more $300 to $400. Yeah. And this, I didn't mention that, but it takes approximately 2 spools of filament, so 2 times 750 grams to print all the parts. So this is also maybe like $60 then. Yeah.
Cool. Any other questions? Let's see. Could you talk more about how the wheels are driven? I was just going to mention, Miro, we're seeing just a kind of a wavy red and blue background there. I'm not sure if that's a secondary screen.
You don't see the presentation?
No, we're not seeing that at the moment. So if you could,
let me just stop.
Yeah, just stop and reshare.
Okay.
Sometimes it gets mixed.
Good. I will share again.
Yeah.
Wait.
Then you can could maybe address the
so what do you see now the screen?
Yes.
Maybe I show it here.
Yeah, so they're good.
Here you see it well. So you see here we have the wheel bracket, the silver part coming down, and then here we have a continuous servo motor, if you want to call it like that. It's a continuous servo motor, a parallax also. And then the wheels, they are installed using screws from the outside. So you mount the flange, and then you screw the flange onto the servo motor, and then you have a kind of like a little bracket that you can screw in from the inside of the wheel, or yeah, you come from the outside with the screwdriver, and this then drives the wheel. And these are actually the same geometry also, these motors. They're the same part, just one is continuous and the other is position controlled.
What was the material of the bracket? Is that also plastic or is it metal? Or?
No, everything here is printed with PLA, which is plastic. Again, this is something that maybe depending on how you plan to use it, I would recommend you to change, because PLA is really good for printing simple parts that are only used indoors. But as soon as you get in contact with water or sunlight or just heat in general, the PLA can deform very, very quickly. So we had no problem with it because we only used it inside, but I know some of our builders, they actually printed everything in PLA, and then in the end, yeah, some parts broke because they used it outside. So maybe think about where you're going to use it, and then choose your material accordingly, and use maybe something more sturdy, like maybe ABS or nylon is even better.
The wheels then cover the motors, so do they protect them from dust getting in there pretty well, or do you have problems over time? Well, I guess most of these would primarily be used inside and not necessarily like out in the dirt or something. I was just curious if dirt gets into the drive motors at all.
So we even had someone drive in the snow. That was pretty amazing. But
That's cool.
I never heard of a failure because of dust in the motor personally. I guess if the motor is somewhat decently sealed, it shouldn't be a problem. But I never heard of that we had this problem, or that someone had this problem. So I wouldn't be too worried about it personally. But if maybe if you go drive on the beach and you really dig a hole with the rover, then it can happen. Yeah.
It's a really cool robot.
Yeah.
Excellent.
We also have Instagram actually, but nobody uses it anymore. So, but if you're into that, you can look. There's some cool pictures. Yeah.
All right. We got in any more final parting questions here?
I'll check the chat again. Huh? Where is it?
So what kind of software, Python or C++?
Yes, in the lab we use C++ primarily, but with this project, because we want to make it accessible, we use Python. And Python is also my favorite language between the two, because it's just so easy to use. So it's all written in Python. Yeah.
You mentioned Ross earlier. Is this a different robot, or I'm sorry I got confused about that?
Ross is not a robot. Ross is a framework where you can basically, it takes a lot of parts, or it does a lot of parts for you that you might not want to code yourself. So Ross takes care of communication between different subprograms. It takes care of how do you make different subprograms? How do you start them separately? How do you make it so you can choose which subprograms you want to start? How do you read in config files? A lot of these functionalities are already implemented by Ross, and that's cool. But what is even better is you have a massive community of people that use Ross. So if you use, for example, an Intel RealSense camera, you don't have to download the driver, write your own driver, write your own interface into the code. No, you download the Ross package, and then you simply read out the messages that you receive from this RealSense ROS package.
So it's acting like the test executive and the environment administrator.
Yeah, it's basically your framework where you program everything in. It's really amazing for big projects. Yeah. So I think for me, any mobile robot should have ROS.
Great, thank you.
You're welcome. Thank you, Steve, for the link. Yeah, it's definitely worth to have a look there.
Yeah, no problem. Any more questions here before we let our presenter go?
Thank you so much for sharing it. That's a terrific project. I'm so happy for your success.
Yes.
I'm happy to share it with everyone, and it was very cool to be here, and yeah, it was great.
We greatly appreciate you accommodating us too. This is, you know, we've been hearing from people from all over the world. It's really been kind of cool just to see what amazing things are going on out there, you know, and then projects like this, you know, this is pretty cool.
Quince is in his bedroom trying to install ROS and GitHub now. Thanks.
You're welcome. Also, have a look at Docker. It's also something that is a bit overwhelming at the start, but it's really something very, 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 very powerful that you can use in a lot of different ways. I can really recommend it, especially if you just want to try out something.
Yeah.
Are your slides going to be on? Are they available on a website or whatever, so that if we wanted to go back and sort of review some of the things you've covered, et cetera, we could do that?
All these things actually, they are on the wiki. So if you go to the link that was shared before, I can repost it.
Was that in the chat, Steve?
I was trying to remember.
It was in the chat, but it got lost when the restart happened.
Yeah. Go ahead and repost it there, Miro.
I will post it.
Yeah. So does that take to an actual, like, this presentation per se? Does that link go there?
No. But
Okay.
if you go to the GitHub, you have way more than the presentation. So
okay.
Do you still see my screen?
We do.
So here you have this is kind of the main repository. And then here you can click on the wiki and you will have everything here getting started. You will see kind of the build plan. Here you can download all the files, the electronic files, CAD files. Then the purchasing instruction will give you all the drawings, all the part lists that you download and show you how to buy all the stuff. Then you have the software instructions where it will tell you how to install everything, all the commands. So it's very elaborate, and really anyone that can read English and knows how to use a mouse can build this rover. Yeah.
Outstanding. Thank you.
Zia has another question I quickly answer. The next for the spot version. So I don't work at ESA anymore, right? So for me, it's kind of a hobby project. So I'm not responsible to maintain this anymore. And actually some people at ESA still contribute a little bit. So I'm not the owner of the project anymore, if you want to look at it like this. So I cannot say what will happen in the future. I did do a design improvement, but I don't have it released yet. And I will probably release it latest, I think, end of February. It will be released. So that's all I know. Afterwards, I think the community will do a lot of changes and improvements, and will hopefully continue with the project. I mean, you see there's 29 forks, so 29 people maybe already modified something. Yeah, but if you're interested to follow kind of what's happening, I think the best is to follow the Discord server, which is also linked
Yeah.
Here.
It's-
It's linked here. You just click, you type in the name, Miro, and then you can continue. Okay.
Miro, I think you are apparently pointing to something with your mouse, but what we are seeing is your mouse roving over a picture that says software environment and shows ROS embedded in Docker.
This is okay. I'm so sorry. Then you didn't see the present what I showed in the wiki. That's not. Oh
yeah,
my God.
so I guess somehow it's amazing that your mouse was moving over the ROS picture.
Okay, that's yeah. Then
Somebody's-
okay. Then everything that I just said didn't really make sense for you. Wow. Okay. Do you see now the screen?
Something's going on here, it says. There we go.
Okay.
So that's what I wanted to show, the wiki
Yes.
on the GitHub.
Yep.
And this is what I explained here. You have really just a whole instruction set from getting started over like the software instruction and how to do everything. And you even have a little Docker tutorial. So if you want to start with Docker, have a look here also.
Okay.
And were you going to post that link again?
Yeah, I think I did, but I can do it again.
He's got,
Is it the Discord link or a different one?
so
Here, it's the GitHub link.
yeah. Okay. So there, yeah. Both of them are on there now. Both the Discord and the GitHub.
Oh,
Yeah.
very good.
Perfect. And you will find both links in both places. So
Yeah.
I can show you the Discord. I mean, you're probably familiar with it. So here.
My when I try to connect to the
Wow.
ExoMy link in Discord, though, it gives me an error and says it's not accessible. And when I
Really?
accept the invite, Safari says Safari cannot open the page because the address is invalid.
Yeah, with this, it
I'm not
works.
sure why that is, but
Then maybe you have the wrong link. Try this one here. ExoPerseverance. So now we can all watch live this guy that built an amazing ExoMy. Wow, what a legend.
Oh my goodness.
yeah, it's really strange. It says 30 people online and it says 299 members, but it won't let me accept it in Safari.
Okay.
My
That is
problem. But
That is actually really impressive what this guy did.
Yeah.
Yeah, so this is why I do presentations like this, and this is why I did the project, because then you see people just build something so cool. Yeah. Very cool. So have a look at the Discord and the GitHub if you're interested. Yeah. Cool. If there are no more questions, then I will stop the sharing. Give it back to you, Steve.
All right.
thank you again.
Yes. Thank you so much. This was.
And if you have any questions, feel free to text me on Discord or LinkedIn or whatever, or GitHub if that's possible. Yeah.
All right. Let's see here. I'm gonna stop that for the moment since it looks like I've closed mine. There we go. All right. Well, thank you again, Miro, for joining us today. And I think this was fun.
Yes.
Okay, if it, yeah, so if any, you know, you can, I think let's see, you've got, you know, it looks like there's contact information out there if you get any specific questions, but it looks like the documentation is got a lot in it, and then there's there's lots of people in the community, so reach out to that community if you want to try to build something like this. Okay, so I think with that we will we'll wrap things up here for this month. Let me just make sure that I'm pull up my when I had to reset my computer there, everything kind of went everything closed up on me. So yeah, okay, so I've already kind of shared everything that I needed to with you guys. Okay, so I'm going to go ahead and stop recording, and we can continue with any sort of discussions here for a short time. And thank you again, Miro, and have a good evening.
Thank you.